I am Evan Hubinger. I'm a safety researcher at Anthropic. I'm going to be talking about AGI safety. So just a little bit about me before we start. So I said I'm currently at Anthropic. I do empirical and theoretical AI safety research there. Before that, I was a research fellow at MIRI, the Machine Intelligence Research Institute, and I did other stuff before that at OpenAI and other places. OK, so essentially what we're going to try to talk about is I want to teach you over the course of this whole sequence how I think about existential risk from artificial intelligence. So what does that mean? So existential risk, we're sort of imagining a situation where humanity is in some sense disempowered, where the future is no longer sort of in our control in some respect. That could be extinction. It could be every single human is dead. Or it could be some other scenario where we lose control, some scenario where maybe there are still humans around, but effectively those humans have no control over the course of the future. OK, and we're going to be focusing on prosaic artificial general intelligence. So what does that mean? So prosaic means we're imagining a situation where we get to very powerful advanced AI systems without sort of any fundamentally new advances in how we're thinking about intelligence. That means we're essentially going to be looking at machine learning, the sort of current broad paradigm of how we do AI, and imagining that that is in fact the thing that gets us to very powerful AI systems. And this sort of notion of very powerful is approximately something like this notion of artificial general intelligence. We're not really going to rely too heavily on this sort of generality notion, but essentially the idea is some system that is approximately as capable as a human across a wide variety of domains. And so that's sort of what we're looking for. We're going to try to understand what these systems might look like, how they might be developed, and why they might be dangerous. And the hope is that this sequence should be accessible regardless of what sort of prior knowledge you're coming into it with. So we're going to really try to cover as much as we can to help people understand. OK, so this is the broad outline for the sorts of things we're eventually going to be talking about over the course of the whole sequence. Today we're just going to be doing 1 and 2. OK. OK, so machine learning. So I think any situation where you want to try to understand what is going to happen with current very powerful AI systems and what those systems might do in the future, we have to start by understanding what it is that the mechanism that actually produces the system. How does machine learning work fundamentally? So I have here what is sort of our prototypical machine learning algorithm. This is going to be sort of what we're thinking about. If this is a little bit intimidating, that's fine. We're going to sort of I'm going to really talk through everything that's going on. You don't have to understand what I put up here. But essentially, what this describes is the process of machine learning, which is we have some function, and that function is parameterized. So there's a bunch of parameters that describe how that function operates. So for example, we can think about a linear function is described by 2 parameters. It's described by the intercept and the slope, among other ways to describe lines. And we're imagining that those parameters are determining how the function works, and we get to search over what possible parameters we want to find a function which results in the behavior we're looking for. And in practice, the way we do this is via gradient descent, where we have this parameterized function, this function that has, in practice, millions, potentially billions, many, many possible parameters that determine exactly how it operates. And we search over the space of the settings of those parameters to find a sort of parameter setting which results in good behavior on some data distribution and some loss function that sort of describes what we're looking for on that data distribution. And we do that search via gradient descent, where we, at each individual point, sort of calculate the derivative of the loss and step in that direction. OK, so how do you think about this? I mean, it's a structurally complex algorithm. I think the best way to sort of conceptualize and think about what machine learning is doing is by thinking about loss landscapes. So what is this? So, well, we can imagine, if you look at each individual parameter, as we're sort of varying those parameters and searching over the space of possible parameters, we can plot, how well does each particular setting of parameters perform on our loss, on our data. Does that particular setting of parameters result in good performance, bad performance? What does it do? And so that's what we have here. We have a sort of dimensionality reduction. We've looked at a couple of particular neural networks, sorts of parameterized functions that we often use in practice. and we want to understand for those particular parameterized functions, for each individual setting of parameters, how well does it do? And so you can see, for example, over here, there's a bunch of these sort of valleys and nooks and crannies where individual parameter points might do really poorly, like out here in the red, or they might do really well, down in the valley in the blue. And the process of gradient descent is effectively rolling down these slopes. So we have this sort of loss landscape that describes, what the different parameter settings do in terms of how well they perform. And we're searching around this space, sort of rolling down, trying to find these valleys that have parameter settings that perform really well. There's a couple of things that I will talk about this sort of particular setup, because it's a little bit disingenuous in a couple of ways. But yeah, question first.
So what exactly are we looking at here? I don't see any like X, Y, Z axes descriptions, and also, yeah, these parameters. Which layer are we looking at in these different networks? Yeah, I'd just like to have a clear vision of what I'm looking at here.
Yeah, great question. So a couple of things. So first is, in terms of like what are the axes, we can think about the depth here, right, is describing the loss. It's describing, and the loss just means how well do you perform on the data set. So we'll talk about some examples of what that might look like in just a little bit. But essentially, we have some set of data, and we want to find a function which does something on that set of data. We have some desired behavior, and this sort of essentially is the depth here is determining how good is the behavior of that particular set of parameters. And the axes are different parameters. So you can imagine, I think in practice, this particular case is a dimensionality reduction, but you can sort of think about this being two parameters. So we have one parameter on X and one parameter on Y that describe two specific parameters that we're searching over. So if this was like a linear function, right, and we in fact just had two parameters overall, then one of these would be all the possible values for the slope, the other would be all possible values for the intercept. And we would just be looking to see which combination of slope-intercept values results in the behavior that we want. And so that's sort of what we're looking at here. In fact, like I said, it's not quite that. So it's a dimensionality reduction, and also, because in practice, the number of parameters is really, really big. We're millions, billions of parameters in these sorts of largest networks, and so you can't just sort of represent it, in this sort of three-dimensional. You need to be able to see in millions of dimensions to really sort of understand what was happening here. But you can imagine the same sort of thing, replicated across many dimensions. In each individual parameters that we're looking at, there's going to be, some, situations where we can sort of fall into valleys in that parameter, these same sort of shapes arise. Now, there are some important facts about the fact that it is so large dimensional. Because it is in fact really large dimensional, there are some things that sort of your intuitions about lower dimensions won't quite work. So, one of the things that we'll see is that it really, changes the volumes of these basins. So, we can think about, this, falling into this particular area, all of these sort of things around here, if we follow the gradient and we just sort of fall down, they're all going to fall into the same basin here. But thinking about volumes of basins in very high dimensional spaces is sort of counterintuitive, because volumes rapidly expand with radius when you have very high dimensional spaces. So, if we, in a two-dimensional space, right, it's proportional to r squared, then a three-dimensional space, it's r cubed. In an n-dimensional space, in a million-dimensional space, the volume is proportional to, r to the millionth power. And so, we end up in this sort of situation where some things can start to get a little bit counterintuitive. But essentially, the idea is that we're trying to look for these sort of desirable basins. Yeah, question. Yeah, go for it.
Yeah, so just to summarize, the blue part is where the loss is better or like lower, and that's where we end up, right? And then, yeah, perhaps as a follow-up question, why the heck is the thing on the left so rugged and like?
That's a very good question. I haven't talked about that yet. I will talk about it. I think it's kind of an interesting thing to note. I'll just mention briefly. I think it's not super important, but basically what's happening on the other side here is this is a particular instance of a case where these are two different architectures, where there are different functions that have been parameterized in different ways. In particular, the actual difference here is that the smooth one has something called residual connections, and the rugged one doesn't have residual connections. In practice, what residual connections do is they substantially smooth out the landscape. Now, it's a little bit disingenuous to say that this is like, fully smooth because it's very zoomed in. So if you were to take this picture and like, zoom way out on the lost landscape, even in the smooth one, you would start to see, more, valleys and stuff, as you look at multiple different basins. But what it does do is it makes it overall substantially smoother, right? So at the same scale, we can see that with residual connections, things are much smoother. And I think that is one way of describing why we use residual connections, right? I'm not going to talk about all of the individual different architectural features that modern neural networks use, but I think one sort of general point is that when people build machine learning systems and when they choose their architectures, what they're trying to do in picking what that parameterized function looks like is they're trying to get loss landscapes that look like that one on the right. They're trying to get these nice loss landscapes that have good properties. In terms of being easy to optimize over, having good minima that can sort of fit all the data. The problem is that task is really tricky because we don't actually understand the sort of mapping between how do I choose a function, a parameterized function, and what sort of loss landscape do I actually end up with? And that sort of disconnect can be quite tricky a lot of times. So yeah, we'll talk about that a little bit. Yeah, question.
So you said that as the dimensions go, the volume of the basins go like r squared, r to the 3/3, and so on. But what is r? Generally, what do we mean by the basins growing, like in as proportion of the whole parameter space? The proportion is going of the space from which you end up in one particular point. Yes, the dimension is going.
Yes, this is a really good question. So I haven't talked too much about like what I mean by basin yet, but essentially we can sort of think about it like this. Gradient descent, right, likes to roll down these hills. It finds situations where we start, maybe at some random point, some setting of parameters that doesn't really describe any particular, meaningful behavior, and then gradient descent, looks at this loss landscape and it goes down. It tries to find these points that actually have good behavior. And a basin is sort of described as the volume where all of the points roll to the same point, right? They all sort of roll into approximately the same area. And so if you think about, here we have multiple basins, right? We've got this like valley on the left, and then we have this like big basin on the right. And those are, if you start on one side, you're gonna end up in different situations. On this side, they're all sort of the same basin. This is just looking at one basin. And so R is just sort of the characteristic size, the characteristic length of the basin. For example, you could think about it as the distance that it takes to roll into the basin. It's getting a little bit technical. It's not super relevant to think about all of this, but basically we're thinking about, okay, we have this we have this parameterized function. It has this really big space of all these possible parameters, and in that space there are these basins that describe various different algorithms that could be implemented by that function. And we sort of want to understand which of these basins do we actually end up with when we do this big search. And we'll talk in a little bit about what are some factors that actually make that determination.
Is there a concrete example of like what these parameters might look like in order to help us get an intuition of what this kind of system actually is?
Yeah, that's a great question. I'll talk in a little bit about some like actual algorithms that the functions might implement and what those might look like. In terms of what the parameters are, they're just numbers, right? They're just floating point values that we use them in matrix multiplications and all of in not just in all sorts of various different ways that the function makes use of them. I mean, you can think about like I don't want to go into too much detail on like exactly the structure of neural networks because I think it's not super relevant. I think the basic we'll talk one thing that is relevant is just like they do sequential computation. So there's a particular computation which is performed, and then based on the results of that computation, it performs another computation, and each computation is parameterized. So exactly what computation it performs is just dependent on whatever the values of the parameters are that determine how it does it. Exactly what those parameters are doing and how they work, I think, is not super important. Yeah, I mean, and many of them are used in different ways. So you have biases, you have if we're talking about like transformers, you have attention heads. So there's a lot of various different parameters that do different things. But basically, it's just some massive parameterized function. And one of the things also that I think is maybe important to point out is that when you have very, very, very large networks, as the sort of size increases, generally they become capable of implementing essentially almost any function. And the functions which you can implement increase as you increase the size. So with really large sets of parameters, you can start finding almost any algorithm which is could theoretically be implemented. And we'll see later that's really important. The fact that as you increase the size of your network, as you increase the number of parameters, the number of possible algorithms which you can implement increases, and you gain the ability to implement fundamentally new sort of structures. Okay, I'm going to move on. I think that maybe this is getting a little bit confusing, and hopefully it'll get a little bit less confusing as we talk about some more stuff. So, okay, great. So here is a concrete example of a situation where you can have a sort of machine learning system, and it finds different basins. So we're going to here's what we're going to do. We have these sort of two shapes. We have the blue blocks on top of triangles, and we have the red Pac-Man with a cape. And the idea is we are going to try to sort of train a network. That is, we're going to search over possible parameterized functions until we find a setting of parameters that in fact is able to, when given the blue block, always result in blue block. And when given the red Pac-Man with a cape, it always results in Pac-Man with a cape. And then we want to ask, what happens if we take that function that we've just learned, and we see what it does if we give it the swapped colors. So what if we gave it a red block on top of a pyramid, or a blue Pac-Man with a cape? And the interesting thing here, right, is that there's sort of at least two different algorithms which you could learn, which would do a good job on this particular data, right? There's at least two basins that describe different sorts of ways that you could fit this data. You could learn a color classifier that classifies any red shapes as one thing, and any blue shapes as another thing. Or you could learn a shape classifier. You could learn the shape classifier that classifies the Pac-Man with a cape in one bucket, and you could classify the blocks on top of a pyramid in another bucket. And so we can sort of think about this in the loss landscape setting as representing two sort of distinct basins that describe two different possible algorithms that you could find when you're doing this search over function parameterizations. And when humans do this, when you ask humans to sort of, what would they sort of classify? Humans generally will go with the shape, though it's a little bit unclear. There's sort of, a reason for this. In practice, if I see a red chair or a blue chair, they both sort of functionally serve as chairs. And so we tend to classify objects based on their shape. But a fact about neural networks, usually at least if you train them from scratch on this task, we'll almost always pick the color classifier. They'll almost always learn to classify the red things into one bucket and the blue things into another bucket. And that's interesting, right? It tells us something about what it is that determines which basins are selected for, which parameterization, which settings of the parameters are the ones which actually get implemented in practice by these networks. Which sorts of ones do they find? And in this case, at least, we know that what they find is they find the color classifier. And this sort of difference, okay, there's multiple different possible algorithms which could learn the data, but in fact, we find one particular algorithm which fits the data, is in some sense the key to what makes machine learning so powerful and makes it work. So we think about, so we can go back to thinking about these basins, right? We can describe each of these different algorithms as occupying these different basins in the loss landscape. Now, in some cases, there will be algorithms which don't even exist in our loss landscape because our model sort of isn't big enough to implement them. But in cases where our model could theoretically implement either one, we have these multiple basins. And the machine learning algorithm has to do some basin selection that determines which of these different algorithms that could fit the data do we actually end up finding. Okay, and there's some research that shows that sometimes there are symmetries between basins, but most of the time we're sort of going to be imagining that we're going to be looking at the sort of desymmetrized basins where we have different basins describing functionally different algorithms.
You described as like the algorithm choosing which basin to use, but isn't it the case from what you said before that we start out at some random point and then we don't really have any control over which basin we wind up in? It's just going to roll downhill?
Yes, that's a really good point. I think that in practice, it's a little bit unclear the extent to which you always end up in the same basin or you end up in different basins depending on the initialization. It really varies based on the particular machine learning setup. I think one thing I will point out, though, is that some things are very overdetermined. So if we think about the color versus the shape classifier in the previous example, the fact that you learn the color classifier in that case is extremely overdetermined. You never learn the shape classifier when you start training from scratch on that task. And we can talk about why that is, but I think that the thing I want to point out that's important there is that even if I randomly initialize, sometimes some basins are so much larger and so sort of preferred by the gradient descent process that we effectively never find the other basins. So in that case, and why is this? Well, we can think about, previously, right? Like I was talking about, what determines the basin volume, right? Well, in these really, really high dimensional spaces, basin volume, can vary drastically between different basins because even small differences in the radius of the basin can have massive changes on the total volume. And so because of that, you can have cases where some algorithms occupy like 10 to the 20 more volume than other algorithms, and there's sort of no chance that you could ever find the smaller basin when that's the ratio that you're dealing with. But that's not always the case. Sometimes there absolutely are cases where there are multiple different algorithms that that are sort of both plausible, and it'll depend on the initialization, which random point you start with, what you'll end up finding.
Does that also depend on the data set that we're providing? Like, for example, we provide different colors of the shapes. If we know a priori that we're looking for a shape classifier and not a color classifier, or would that require us to know all the confounders kind of in advance?
Yeah, that's a great question. So if you give it a bunch of instances of cases where you have the same shape but a bunch of different colors, and you tell it to find an algorithm that classifies all things based on shape and ignores the color, you absolutely can learn shape classifiers. But the question, and so it totally depends on the data set. In this case, though, we're sort of asking, well, what if we don't give it that information? What if we sort of don't say whether we're asking for color, we're asking for shape? We sort of just want it to figure out what is the best algorithm for distinguishing between these two things, and then we sort of ask, what it learns in that case. And I'll talk about it a little bit, but I think that distinguishing, the ability of the machine learning algorithm to pick, which algorithm does it like better to solve the problem is really critical to why these things are able to do what they're able to do. Because you can imagine if they just memorize the data exactly on every point, that would do a good job at fitting the data. Any data you give it, if it just memorizes every data point, it'll always be able to do 100% perfect performance. But it's useless, right? A 100% memorizer that has no ability to do anything coherent on any new data points doesn't do anything structurally useful for you. And so the fact that machine learning doesn't do that we don't just learn this memorizer, that we learn something that has an interesting structure, that actually implementing something relevant, like distinguish based on color, is what makes it powerful and useful.
Is it possible to implement the same algorithm but with different weights, such that, if we are in such case, we have different weights, but basically the same algorithm, does it mean that we have landed into the same basins or into different basins, but which are equivalent in terms of loss?
Yeah, that's a really, really good question. So in fact, there's some research that shows that the fact that there can be cases where the same set of weights will implement, different sets of weights will implement the same algorithm, is a really important facet of which basins sort of end up being larger and which basins end up being smaller, which algorithms sort of end up being favored. Because if you have an algorithm and the same basic algorithm can be implemented in a really, really large number of different ways, then that algorithm becomes much easier to find, and so it becomes favored by the gradient descent process. It becomes that sort of basin becomes very large because there's all of these different sort of effectively equivalent parameterizations which result in the same functionally equivalent sort of model. And so we think about something like the color classifier. One of the ways we can understand, why does it learn color is, well, color is, an algorithm that is sort of relatively easy for it to calculate based on the RGB values that it's sort of taking in. And there's a bunch of, other stuff that it, it doesn't really matter. It only takes a small number of parameters. The rest of the parameters can be set to essentially anything. There's a bunch of ways to, calculate the color, looking at different pixels, looking at different places on the image. And so it's not sort of, there's so many different ways to implement it, and it's so simple based on the data that it's sort of input that it's receiving, that it sort of ends up being, a substantially larger basin that's sort of favored by default. Yeah.
So one thing I read last year was this idea that the algorithms that were most likely to be selected were the most compressible. because they could be done in the fewest parameters, letting the other parameters be basically whatever they wanted. Is that related to this idea of basin volume?
Yeah, absolutely. So I think that we're going to talk a bunch about why simplicity is, a really important component of, what selects which algorithms you end up learning. And simplicity, functionally is essentially the same as compression. It's just, how, can I take it? Can I, find some really functionally simple algorithm that is able to explain all of my data? That's sort of what a compression is. And so compression is absolutely, an important part of what's happening here, right? Now, how it maps from simple algorithms to large basins and things which are favored by gradient descent is a little bit complex. There's a bunch of different things that go into that. So one really important facet is what I was just talking about, which is the fact that when you have a sort of structurally simple algorithm, it leaves a lot of parameters untouched. Or like not relevant, or there's like a bunch of different ways to implement it, which means there's a lot of different points in the weight space which all correspond to effectively the same algorithm, and that means it has a very large basin. So that's one of the factors, but there's other factors as well. One other factor is that we often will do explicit regularization, where we will actually like take the function and we will explicitly say, we want functions which do better on the metric of being small and simple. And the reason we do that is the same reason we did the residual connections, right, in the previous thing, where we really, the reason that machine learning is so powerful, the reason we want to do it is because we're hoping to get these simple, structurally simple algorithms out of it. And the best way to get those structurally simple algorithms is by, using these techniques that help us find, structures that in fact result in these simple algorithms. And so that's why we do stuff like regularization. That's why we add things like residual connections to get these loss landscapes that have the sort of simple algorithms favored.
I think I'm wondering about now is when we got these bases, is there a way to tell which algorithm they will implement? My current model of this looks like, oh, we've got these points or like these basins in parameter/loss in the loss landscape, and then those all kind of show which parameterizations perform well on our given tasks. So for the classifier, the large basins will basically result in a classifier that has a high accuracy. But the way it does that is still kind of obscure to us, right? Does it do it by form classification or like through the colors? And now my question is there a way to actually tell just by looking at the basin what kind of algorithm it is implementing?
That's a really, really good question. And I think the unfortunate answer is oftentimes no. If only thing I know is, okay, it's some setting of parameters, and that setting of parameters looks like it does a good job on the data, that's often all I know. I know that in some sense, okay, I know that this whatever algorithm I found corresponds to a large basin. It corresponds to some sort of structurally simple algorithm. But I don't often know what algorithm it corresponds to. Now, sometimes you can figure it out. So in the shape, color example, it's pretty easy to figure out because we just give it a new example. We give it a case where the shape and the color are different, and we see what it does, right? And so we can tell, in that case, what it's doing. And sometimes you can do that, to tease about different differences in algorithms. But sometimes that gets really hard, There's just a lot of various different things to test on, and it can be very difficult to, form a hypothesis about what it's really doing. So we'll see in a little bit, an example of a case where we can do transparency. We can actually sort of look inside the model and, see what algorithm it's implementing in a particular case. But that can also be really hard because oftentimes, interpreting what these parameters are actually doing is really difficult because, they're not selected to be interpretable. They're just selected to be whatever, is the low point on the basin. Whatever set of parameters in fact results in good performance. And so, there's no reason that we would be able to understand what they're doing. In some cases we can though. In some cases we can see, it's implementing this sort of simple, algorithm that we understand. We'll see an example of that in a little bit. But that's not always the case. Sometimes we can understand and sometimes it's really difficult. Hopefully if the field of transparency progresses, we can get to the point where we can sort of always look at a set of parameters and understand what it's doing. But in general, right now, there isn't really a way for us to do that. Okay, so I talked about this already, but the thing that is so important about this basin selection, about this idea of figuring out which setting of parameters you want, is, structurally, this is the thing that makes machine learning, so good, what makes it what it is. Because if I imagined an alternative process, right, that, just took, I saw these red data points, right, and I was like, okay, here's how I'm going to fit the red data points, right? I do this, crazy blue, line, right, that goes up and down. We know that that line is wrong, right? Wherever this data came from, wherever, I collected these red data points from, it probably wasn't from that distribution. It probably didn't come from a line that looked like that blue line. And we know that because, something like Occam's razor, right? In fact, real-world data, real-world patterns that actually exist tend to have these simple explanations. They tend to have, generating procedures behind them that have some structurally simple pattern that describes what's going on. And so the magic of machine learning, the thing that's so powerful about it, is that we don't just find any function that fits the data, right? We have these procedures for finding simple functions that fit the data, functions that are sort of structurally simple explanations for what's going on, this green line here, that are actually likely to do a reasonably good job if we give it a new data point. And so, what simple means is a little bit weird, right? So it's not the same as always what simple means to a human. So if we think about the, color versus shape classifier, humans will often pick the shape, but the model will almost always pick color. And so, it's not quite the same, but it is, something that is, very important here because we have selected our machine learning models. We've found the architectures that in fact result in finding things that are simple in the sense that they do a good job. Simple in the sense that they actually fit real world data. They actually describe real world patterns. Okay. Okay, so I promised an example of a sort of, transparency of a situation where we can actually look at what these sorts of simple algorithms, in fact look like in practice when they're implemented in, a neural network. So this is an example of a case where we took, a very large parameterized function, in this case, a convolutional neural network, and it was trained on ImageNet, which is a class, a problem. We were trying to classify a bunch of different images. So you've got cars and cats and dogs, and you have to be able to distinguish between each individual one and tell, which is which. And so we've trained a very large network to do that task, and we want to know what's it doing, right? And this particular case is, we're trying to understand how it classifies cars. So it has one particular point in the computation where we can sort of ask, okay, what image would most, cause this particular part of the computation to be large, to really, activate. And we find this sort of, image that sort of looks like a car. And, the conclusion is, okay, this is sort of where it's doing the computation that determines is the thing a car or not. And so you can sort of think about this image as the maximally car image. This is, the image that this neural network thinks is, the most possible car. And an interesting thing from this is that you can sort of see, I think, if you sort of squint at this, what it's doing, right? Like what actual algorithm is it implementing for car detection? If you have not seen this before, you can try to think a little bit and guess as to what it might be. So I'll give a couple seconds to just sort of think about that. But I will reveal the answer, because what we can do is we can actually look at the inputs. So we can see, okay, because the algorithm operates, the particular parameterized function that we found, it operates in these sequential computations. It first does one computation and then it does another computation. We can see, okay, what are the computations that happened before this, and what are the sort of images that maximally activated those computations, and we can use that to help us understand what this computation is doing. And so if we look, we can see. And I think it's pretty clear, based on this, what it's doing. So the images on the top are sort of what it's looking for on the top of the image, and the images on the bottom are what it's looking for on the bottom of the image. And it's pretty straightforward. It's looking for windows on the top and wheels on the bottom, and that's what a car is to this neural network. It's determined the algorithm. It's found this sort of structurally simple algorithm for finding cars, which is look for windows and then look for wheels. Yeah.
Those blank things in the center, are those just not shown, or does that mean the algorithm doesn't care what's in the center?
It means it mostly doesn't care. It's saying that whatever is in the center of the image, it's not really looking at. It's not using that to determine whether it activates or not. And so Yeah, so you can see in this case, it's really looking, very concretely for two very specific things. It's, we have in the previous computation, it did some computation to determine what a wheel is, and it did some computation to determine what a window is, and it's looking to see, is there a window on the top, and is there a wheel on the bottom? Okay, and so this is pretty cool, right? It's showing us, this concrete example of, something, a little bit more complex than just the, the color, the shape example, where our neural network, we found a particular parameterization by searching this big parameter space to find some setting of parameters that is, has some large basin and does well on the task. And we found this structurally simple algorithm, right? We didn't just find some, memorize every picture of a car you've ever seen. We found some algorithm that actually, is doing some structurally interesting thing that is able to generalize, right? This is an algorithm that if I give you a random new picture of a car, it's often going to succeed. Sometimes it has, cases where it might fail. Maybe I've removed all the wheels from a car, and well, it's still a car. And in that case, maybe this would fail. But in general, this is a structurally, simple algorithm that is actually performing the task in generality. And that's what we're trying to get, right? That's the thing that machine learning is doing. It's trying to find these structurally simple algorithms that are able to solve the task in generality, so that you can find algorithms that actually generally do a good job. Okay. So I want to talk about another thing that's a little bit interesting about a particular fact about this notion of simplicity, because I think it's sort of counterintuitive, which is that this sort of notion of simplicity, right, of finding these sort of structurally simple algorithms to solve tasks, is something that actually, when we build larger networks, when we build bigger networks with more parameters and more data, when we build larger networks, we often are doing it for the purpose of finding simpler algorithms. And this works, right? When we have larger networks, we actually find that they do often learn structurally simpler algorithms. So this is a little bit confusing, right? So, okay, they have more parameters, right? So in some sense, a larger network with more parameters, it requires more things to describe it, so it must be more complex, right? And in some sense, that's true, right? It is the case that if it has more parameters, it takes more things to describe, it's sort of more complex. But it might be learning some algorithm which is structurally more simple. So you can think about, let's say I had a network that all it could do was, one sequential computation, right? It can't learn, if it can only do one sequential computation, it can't learn something like look for windows on top of wheels, because that's an algorithm that really requires you to be able to first do the wheel and the window computation, and then combine those into the windows on top of wheels computation. And so if you're only doing something very short and simple, you can't learn that algorithm. You're going to have to learn some sort of maybe more brute forcey, memorizing sort of thing. And that sort of brute forcey memorizing algorithm isn't structurally simple in the way that the windows on top of wheels algorithm is. And so even though the windows on top of wheels algorithm maybe takes more parameters to describe, the actual sort of fundamental algorithm that it's implementing is simpler. It's doing something that is sort of structurally simple. And we can think about this in a sort of Occam's razor sense, right? So Occam's razor says that in practice, real-world data is described well by the simplest algorithm that fits the data. And that's sort of what we want, right? If we believe Occam's razor and we have some data and we want to do, find the real-world pattern behind that data, then we want the simplest algorithm that fits that data. And when we have larger networks, we sort of increase our search space. Now we can search over even more possible algorithms. And that unlocks our ability to find algorithms that are sort of structurally simpler than any of the algorithms that we previously were able to search over. And so we can think about it as, well, we're still trying to find the simplest algorithm, but now we're trying to find the simplest algorithm in a larger space. And that means we can do a better job, because the simplest algorithm in a larger space can be simpler than the simplest algorithm in a smaller space. So I have an example here of what that looks like in practice, but here, question.
So does this mean that in general, as models get larger, they actually become easier for us to figure out what they're doing and what's going on?
Yeah, that's a great question. And the answer is maybe. I think it's really unclear. So Chris Olah, who's the head of interpretability at Anthropic, has a sort of hypothesis about this, which is, what happens is, first, as you have networks like something super simple parameterized functions like linear regression, right, where it's just two parameters, it's really easy to understand because it's so the function itself is sort of structurally simple. But then as we introduce more parameters, it starts to get less and less understandable. But the idea is, like you're saying, as we keep adding parameters, it'll start to get more understandable again, because we're starting to learn these sort of simpler, human understandable algorithms. One concern, though, and this is sort of what Chris hypothesizes will happen after that point is that at some point you start to learn algorithms which are sort of simple in a human sense. They're algorithms which are structurally simple, and they're algorithms which are structurally simple in a way that we understand them. They're the sort of simple algorithms that we learn, that we use, right, when we try to understand things in the world. But at some point, you start to surpass the best algorithms that humans use, the best algorithms that we use, that we understand. And you start to get to algorithms that are structurally simple in some meaningful way, but in a way that is not the sort of algorithms that humans often use to sort of classify and understand the world. And at that point, it's sort of unclear. Maybe at that point, it starts to become less interpretable again. That's all conjecture, though. We don't really know. So what we have seen is that, I think the sort of broad strokes of what I just sketched out about the sort of starting part of that curve seems to be broadly correct, where a lot of really, really early algorithms are very easy to understand, and it gets harder, and then it gets easier again. I think one tricky thing is that there's been a lot of that sort of work was done originally on image networks, like with the windows on top of wheels, and it gets trickier for other sort of models like language models, which we'll talk about later. But I think it's unclear, and it's the best answer I can give is just more research is needed. We need to if we do more interpretability and we start understanding more about when is it the case these systems are understandable, we can learn more about this. And right now the best I can offer is like some speculation, anecdotal evidence, what sorts of things we've seen and what general trends. We don't really know what we're gonna find. Question? Oh, you've got it already. Great.
So I'm going to interpret the graph on top. It looks like at the beginning, perhaps the model's underfitting, and then there's this point around like 100 or 110, where the loss begins to rise again, and then it at a certain point begins to drop off. And I guess I'm wondering, is the way to interpret this that there's like two competing forces, like the one where you described, where a larger model is able to, I suppose, search over more algorithm space. And so you have like overfitting happening at first, and then this ability to search for more space takes over at a certain point.
Yeah.
The overfitting stops. Is that?
So I've had this graph up now for a while, and I haven't talked about it. So that's my bad. But so let me try to give a little bit of how I think about what's going on here. So so first, just very briefly, so what's on the top and what's at the bottom? So on the bottom, we have training loss. So what this describes is it describes how well does the particular setting of parameters that we found do on the data that it has seen so far. So on the data we've actually given to it, on the data that we actually have available, that we're sort of training it on, how well is it doing? And we can see that as we sort of change the size of our model, this is a particular type of size, we're holding everything else fixed, we can see that as we increase the size, it gets better at fitting the data, right? The data that we've actually given to it, it's able to fit. We're able to find some setting of parameters which does a good job on that data. Okay, but now we have to ask the question, right? How well does it do on data it's never seen before? And in this particular case, this is a translation model, so we're trying to get it to do a translation task. And we want to understand, if I give it a pair of sentences in English and French that it's never seen before, how well does it do on those sentences as opposed to the ones it has seen? And the answer, like you were pointing out, is well, it's a little bit weird. So it starts out doing very poorly because higher loss is worse performance, because it starts out at some random algorithm. And when it just has some really small embedding dimension, right? When it's just a tiny model, it basically can't implement anything useful or interesting, right? And so it's doing the best it can, but the best it can is not something very, very meaningful. But as we increase the size of the model, it gets drastically better. And so we find an algorithm that is sort of able to sort of fit and understand what's happening here. And then it gets worse again. So we start getting into a regime where the performance degrades. And then as we keep getting larger, it starts to improve again. So what's happening here? So a couple of things. So first, let's start with what's happening in this first basin, or this first sort of, this part here. What's happening in this part is structurally where we started with we have a situation where it's not possible, to actually find any setting of parameters because our thing is so small that fits the data perfectly. And so because we can't find anything that fits the data perfectly, it's sort of forced to find something which is simple via the, just the brute fact that it can't implement the memorization, right? Even if it wanted to memorize the data exactly, even if it wanted to just, memorize every, sentence it's seen, it can't do that because then it's not big enough, right? It doesn't have enough, parameters to actually memorize the data. And so it's forced to implement this sort of simple, some sort of simple algorithm instead. Okay, but then we give it more parameters, right? And what it does is once we give it just enough parameters that it's able to fit the data exactly where the training loss goes to 0, you can see that that is the point where the green corresponds to green and purple corresponds to purple. That's exactly the point where we get the worst performance on the test data set, the sort of held out data that it's never seen before. So what's happening? Well, what's happening is when we get to this point where it's just barely large enough that it can find something that's able to fit all the data, well, in that situation, there's basically only one thing that it can learn. It can learn to, it doesn't sort of have to have a choice from a bunch of different possible algorithms where it can pick the simplest one that fits the data. There's just one algorithm. It's just essentially a memorization algorithm, right? It's just barely large enough that it can memorize all the data points, and it can't do anything else. It's not big enough to be able to learn some, structurally simple algorithm that's able to sort of, solve the data in a meaningful way. And so because of that, we just end up with this poor performance. But if we keep making it larger, we get better again. Because if we keep making it larger, now there's a lot of algorithms in the space that all sort of have a good performance. And it can pick from among them, whichever one actually is simplest, whichever one actually, has the largest basin, whichever one actually is sort of effectively doing, something which is structurally simple in a way that is able to generalize to these other, new settings that it's never seen. So I will point out that, a lot of this is not super well understood. A lot of the stuff I just said is some amount of it is conjecture. I think that a lot of it, though, is pretty well supported by the literature on this question. This specific phenomenon is called double descent. And another thing I will point out also is that in practice, you don't always want to be in this regime. So sometimes you'll want to be in this basin, in this case here, where you're early on, and you're simple because you're just sort of too small. And sometimes you want to be in the other case, where you're simple because you're too big. But in either case, you're sort of selecting it to be simple. Now, one thing I will say is even when you're in this sort of early basin, where you're sort of simple because you're too small, as the amount of data that you have increases, this basin sort of moves to the right. And so you have to make your model larger and larger and larger and larger to stay in this basin also as you get more and more data. And so it's still the case that we sort of, as we get more and more data, we sort of want larger and larger models, more and more parameters. Even if we're in this case, and certainly if we're in that case. Questions?
So earlier you said that machine learning models seem biased against finding this memorization-based pattern. So why does that seem to happen here and not in other circumstances like the car example?
Yeah, that's a great question. So what's happening here is we're sort of forcing it to. We've sort of put it in a situation where it's just barely big enough that it can fit the data if it devotes every parameter to memorizing it exactly, but it's not large enough. It doesn't have enough parameters to sort of represent anything, sort of more interesting than that. And so because of that, one of the restrictions, right, is you can think about the machine learning as well. It tries to find this, this simple basin, but it's always going to find, some basin which actually results in good performance, right? If there's nothing, if all of these sort of possible simple things that it can find that it has available to it, none of them actually do a good job on the data, well, then it's not going to find them, right? It's only going to find things that actually, in fact, do a good job. And so you put it into this situation where it doesn't want to find these sorts of, things which are, memorizing, but we've sort of forced it to because it's sort of the only option in the space available to it. That's sort of the theory for what's going on there.
I'm still not quite so sure what happens when we extrapolate this even further. So we are cutting this graph off at a hidden dimension of about 500, but today's transformers are much larger, right? Is there something on a paper that looks into what happens when we actually drive it even higher? And in that regard, also one observation here is that the test loss doesn't seem to dip below its initial a low point. Is that something that you can make do with by increasing the hidden size?
Yeah, if you keep making it larger, at least along it's a little bit unclear if you're just looking at this one particular dimension, but if you're just making the model overall larger, yeah, you will eventually reach substantially better performance than any other point by extending this graph, out in that direction. I will say, so in practice, yes, we do things that are much larger than this. We also do a lot more data than these were trained on, right? So that changes the overall structure of the graph. But yeah, it is absolutely the case that, and this is pretty well studied, that you can sort of replicate this in many different contexts. Though exactly where you'll find each individual point will vary based on the amount of data that you're using and stuff like that. But yeah, if you keep going, you will start to get even better and better performance. Most of the time, because the sort of compute efficient point often will end up being relatively early in this graph. But that's because you have huge amounts of data that sort of push the whole thing out, and then we sort of find something relatively early on that is able to fit the data. And you can think about, like I said, both of these are sort of valid strategies for sort of finding simple algorithms, either being really early or being really late. You just sort of don't want to be in the middle. In both cases, what you're doing is you're sort of trying to find something which is structurally simple and able to fit the data. And the question is just sort of where is the best place to be on this graph to find something which is structurally simple. Now the important point though, the takeaway sort of that I want here is just that when the reason we build these larger and larger models, the value of them is that they are generally able to help us find these more structurally simple algorithms. In both cases, either whether we're way over there or whether we're over here, in both cases, the larger models help you find simpler things, because as I have a larger and larger model, I can use more and more data and find some simple thing here, or I could push it way over there and find some simple thing over there. In either case, what we're doing is we're sort of by having a much larger space of possible algorithms to search from, we can find ones that fit the data and yet are still sort of structurally simple in a meaningful way. Question?
It's a little counterintuitive to me in some ways, because in like traditional machine learning, larger models we sometimes think of as finding a more complex solution, whereas here you're saying that larger models are able to find a simpler solution. And I'm wondering if there's something fundamentally different about neural nets or transformers, or am I making a false comparison between parameters in the sense of the neural net and complexity, or largeness in the sense of a simpler algorithm?
Yeah, so you're definitely, so the thing you're saying is totally valid. And the sort of classical machine learning take would just give you this part of the graph, this early one, and would not give you the later part. And so the later part is a little bit confusing in that it's sort of unique to machine learning. But what's happening here is fundamentally not that complex. So what's happening is that what we're doing is we sort of are doing what's what the sort of authors of the original double descent paper called this is interpolation, where the idea is that in sort of the standard machine learning sort of in the standard like classical paradigm, the idea is, well, we just have some space, and we're just gonna we're gonna take the space and we're just gonna select those algorithms which in fact do a good job on some data, and because of the finiteness of our space, that gives us some guarantees about how good those algorithms have to be on new data. That's sort of not what machine learning is doing, right? The space is often so big that it's not the case that we're sort of getting our guarantees from the finiteness of the space. The reason that it does well is because of this sort of basic difference between some algorithms being favored to be implemented and some not, right? So some basins being larger than others, some things being have many possible parameterizations to implement them. And so what you can think about this as happening, right, is that what's really going on is that rather than sort of just doing this sort of finite space thing, it has a basic prior that describes for each individual type of algorithm how simple is that algorithm, how reasonable is it, how structurally useful is it. And what machine learning does, what we've been able to find these architectures and these search processes which result in being able to select out the algorithm which is sort of does a good job on the data while also having those sort of properties that are sort of being selected for by the structure, right? That are in fact simple algorithms. And because of that, that's where we get our guarantees, right? The reason that it generalizes is not because we sort of forced it to by selecting from some small space, the algorithm that actually had good performance. It generalizes because the real world actually has the property that it is simple, right? And so you can think about this as, the guarantees of machine learning, the ability to sort of learn algorithms which actually work in practice in the real world, wouldn't work if you were in a world where real world data wasn't simple, right? If you were in a world where like real world data was just like totally randomly selected, it would not be the case that you would see any of this, right? You wouldn't be able to, machine learning wouldn't work in the same way. You wouldn't be able to find, this sort of property where you can just sort of, take these sort of things and find the big basin and that actually does a good job. And so, because of this, it's not coming from the sort of basic mathematical property about like, this sort of these finite space properties. It's instead coming from this sort of property of the world that like, real world data actually is simple, and we're able to find, things that are biased towards simple algorithms. And that's why it does a good job. And so in that sense, it's sort of in a different regime. It called this interpolation, right? Where it's like we're trying to sort of take data points and find the sort of simple thing that goes between those data points, right? Rather than trying to just sort of like fit in some sense. The sort of classical regime. Yeah.
I believe last year there was a paper called Chinchilla, which showed that modern language models were undertrained in terms of the data they use, and they should actually be smaller, but they train on a lot more data. Is this basically showing that they could go further before they reach that first optimal point on this graph?
Yes, that's a good point. So I won't go into too much detail on the structure of the scaling laws. But what Chinchilla was showing was essentially that if you do your training right, because there were some sort of problems with stuff like the learning rate schedule in the original scaling laws paper, you can make it so that the sort of where you find the sort of optima and what the slopes are ends up being different, such that what they're sort of trying to calculate is the sort of compute optimal point. So how many data points, how large of a model should you pick to find the best performance, given that you have a budget in terms of how many GPU cycles are you willing to spend. And that ends up being a little bit tricky. It's often very dependent on like how we do sort of computation. But one of the things that Chinchilla shows is that there are these relatively natural scaling laws where the ratio of the amount to which you should increase data and the amount to which you should increase the size of the model actually, when you do it right, ends up being 1-to-1. You're sort of you sort of increase them together in this sort of fixed ratio. And so this is an interesting fact that sort of Chinchilla has found. But it's not super relevant here. It's just like, okay, if you were sort of to think about what happens when you sort of scale these graphs up and you look at the trends and sort of where things end up, what sort of trends do you generally see? But the trends hide a lot of things. They hide a lot of, okay, what's actually happening in practice in terms of what algorithms we're implementing. One thing that's kind of fun is that if you look at this graph, you can see there's this little bump right here. And at the time when this graph was made, I don't think anybody really understood what this bump was. But I think I can say with relative confidence that we now understand exactly what's happening here. It's learning a particular type of algorithm like the Windows on top of wheels algorithm called an induction head. So there's a paper that finds that actually when you do language training, you almost always see a bump around here that describes the formation of a particular type of algorithm. So it's pretty interesting. What's sort of happening when you sort of look at the individual details. But when you zoom out, you can see these sort of nice scaling laws that describe these sort of general properties about as we change the data and the model size, how are we changing our ability to find simple algorithms that fit the data in general? And those sort of properties tend to be relatively continuous and predictable. But the actual algorithms that it ends up implementing are oftentimes can vary a lot. Cool. Okay, another nice example of what's happening in this sort of particular case of when you have really large models is grokking. So this is a case where you take a arithmetic task. So it's just sort of trained on a particular mathematical task, and we have the sort of training loss in red, or or I guess this is accuracy, not loss. So higher on this graph is better, where originally, after some number of steps, it learns exactly, to fit the data perfectly. But on the held out data, it's learned nothing. It has no ability to find any algorithm which is meaningful to solve this larger data because it's effectively just memorized something. But if you keep training for long enough, eventually what you find is that it does learn it. It does find the structurally simple algorithm which is able to solve the task. And so, what's happening here is this is another case where it's, as we train for longer, as we have larger models, we're able to find these sort of structurally simple algorithms. And once we've found them, they're sort of these really powerful, basins, these attractors that, we can stay in and can really help us solve problems. But they take these, oftentimes really big models and a lot of search to actually find things which successfully are able to learn these sort of structurally simple algorithms. And so in this case, it takes a really long time and a lot of optimization before it finally clicks and learns the actual sort of structural arithmetic algorithm which solves the task. And so that's what's happening eventually here at the end. But it can sometimes take a lot of search around the space until it finally finds this this sort of basin which actually has this sort of structurally simple thing. Yeah, question.
Looking at the loss or state graph, but for the loss, is it looking the same way, or is it like the same kind of trend, or if we're looking at the loss instead of the accuracy here?
Yeah, if we're looking at the loss instead of the accuracy, it would look very similar, just inverted. Yeah, it's very similar.
We're trying to optimize for training loss in terms of our gradient descent. How is it that the AI doesn't just get stuck at a point where it never learns anything? How is it that eventually actually does learn to generalize despite not really having any more gains to be made by doing so?
Yes, that's a great question. So I think that what's happening here is it's not just optimizing right for performance, right? It is in some sense sort of looking for things which are simple, right? And so the question is well, how is it looking for things that are simple? And it's a little bit complex. There's multiple different factors. So one factor is just the fact that we do regularization, right? So we actually have regularization is just the process of we force it to learn simple things, right? We sort of force it to find algorithms which are, have small values for the weights so that they're, smooth and continuous. And so what that means is it just has to keep searching a lot until it finds something which actually is, able to have small, simple weights and still, simple, parameters. Weights are just the parameters in the parameterized function, which in fact result in good performance. And so regularization is an important component of this. But also just stuff like Basin volume, right? Where it's okay, as it keeps searching around, structurally simpler algorithms have this property that they're sort of attractors in the space, right? That once that they tend to occupy larger volumes, they're sort of once you find them, you sort of tend to stay there. And so as we keep searching, we can find these sort of structurally simple things, because of those sort of basic properties of the space. Yeah, question.
You say that structurally simple algorithms have huge basins. Can you help me understand why is it true?
Yeah. So great question. So it's a little bit unclear. I think that everything I'll say was just sort of some speculation, but I think there's a couple of things that we can point out. So one thing that I was talking about a little bit previously is this idea that when you have simple algorithms, there's more ways to implement a simple algorithm because if I think about it, let's think about it this way. So let's say I'm only using half the weights because all I have to do is implement this relatively simple thing that only takes a couple of computations, and the rest of them basically don't matter. Well, if they basically don't matter, then that means any possible value for them is all in the basin. All of the values of those remaining parameters all end up in the same basin, and so because of that, it ends up occupying a very large volume. So that's one reason, right? The sort of possibilities of redundant parameters. Also, algorithms that have symmetry. So if there's two different ways to implement the algorithm that's sort of effectively symmetric with each other, then both of those will sort of occupy the same basin for that same algorithm. And so algorithms that are sort of very symmetric, that have the property that there's multiple sort of symmetries in how you implement them. Something where it's if I sum a bunch of numbers, I can either start from the left side or I can start with the right side. There's multiple different sort of similar ways, symmetric ways to do the same algorithm. Those will end up having multiple ways to implement it in the same basin. And so those are some factors, right? That there are multiple ways to implement it that can yield these sort of simpler algorithms that have larger basins. And also other factors like just the regularization, right? We force it to try to find parameter, algorithms which have the low parameter values. We often do stuff like dropout, where we actually will take some parameters out randomly and force it to still be able to work even if we remove parameters. And so that forces it to sort of have to find things which aren't these sort of super brittle algorithms. And so we one of the really important things here is that it's not just that we humanity just stumbled upon some way of doing machine learning which just magically always results in simple things. That's sort of true. But an important part of the picture is also, well, we wanted it to find simple things, right? The reason that we do machine learning in the way that we do it is because there has been, years and years of progress on trying to find the particular ways of parameterizing functions, which in fact have the property that when we search over those parameterizations, we find simple functions, right? Because that's the thing that actually gives machine learning its power, its performance. It's what lets it, find these interesting functions that are actually able to solve complex tasks. And so that's an important part of the story as well.
Intuitively, it seems to me like dropout might lead to a more complex algorithm. Like I'm imagining I've got a 4-step process to solve a function, but if one of my steps might just stop working 10% of the time, I feel like I would need a more complex solution to actually get to the right answer every time. So why does Dropout actually simplify these algorithms instead of making them more complex for the need for redundancy and the like?
Yeah, that's a really good question, and I think not one I have a super satisfying answer to, because I think the problem is, we don't actually really well understand exactly what it does do. Things that we do understand are oftentimes it does seem to improve performance, and not just train performance, right, but test performance. And so to the extent that we believe that like real world data is actually distributed according to something like simplicity, that means by Occam's razor, it has to be learning something simpler. But that's obviously not very satisfying. We really want to understand, well, okay, why? How is it learning some simpler algorithm? And it's a little bit unclear, right? So I described something in broad strokes that's like, well, in some sense, if it's really brittle, that's a really complex algorithm, because simple algorithms should have this property that they're sort of continuous, that they don't depend on like tiny little pieces. Now, is that true? I think one of the ways to think about this, right, is that when I say simple, right, what I mean is not the same as what it means, right, to humans, right? Simple is in big quotes here, because simple is just whatever the actual property is of the world that results in having algorithms which have that property do well, and whatever property it is of neural networks, which in fact results in it being generally finding algorithms with that property. And so we can't always sort of interpret it in the same way we would try to interpret sort of our notion of simplicity. And especially in the case of Dropout, yeah, I agree that the thing you're saying makes intuitive sense, and I wish I had a really nice, satisfying answer to why. Like, okay, but actually the notion of simplicity doesn't work that way. But I don't. I think we just actually don't really understand, super well exactly how the, these sorts of, biases work. Yeah.
I remember reading a paper from 2016 by Zhang et al. About generalization, and in this paper, it was kind of strange because they showed that you could train a convolutional network to fit noisy data entirely, and if you train the model to classify proper data but with also partially noisy data, it first learned to properly classify the real data and then overfit to the noisy one, which seems to imply that it learns first the simple algorithm to classify the data well, and then have to rely on overfitting, which seems to be the opposite of what's going on with grokking. So do you think it's because of, in the case of grokking, modular division, it's harder to learn than learning the data by heart?
Yeah, so this is a really good question. So I think that what I would say there is what's happening is that it's this graph here, this thing that we call double descent, where when you're early on, right, when you're in this initial regime, then what you're doing is you're sort of as you keep making it larger, as you keep training, you end up in a worse spot because you sort of do this overfitting, where you end up learning just sort of memorize a bunch of data points. But if you kept going, you probably would eventually see that the second part, where with even larger more training, you would start to do better again. Grokking is just sort of a very extreme example of that. If you look closely, you can actually see that there is a double descent, right? Where you actually, you do go up and then go back down again. And then eventually you just have this very extreme thing at the end where you find the sort of exact simple algorithm. What the shape of that sort of double descent curve is and how it looks will vary in the particular setting. But yeah, I think that basically that's a phenomenon that's going on there. Okay, so we'll talk a little bit about what this looks like in practice. So, we've talked a bunch about these sort of relatively simple classification problems, cases where you just have, shapes and color, or, where you're just sort of trying to solve some relatively straightforward classification problem like that. In practice, that's not always how we use these sorts of systems. So, one example of a thing that we will often do is reinforcement learning. I think you should not think of reinforcement learning as really fundamentally different than anything we've talked about so far. Structurally, it's doing something very similar. So what we are doing is, rather than searching for the function which sort of has the best performance on the data, we're searching for the function which, when it acts in some environment, results in the best performance in that environment. So we're sort of, instead of searching for the sort of simplest function which does a good job at doing classification of images. We're searching for the simplest function that, when you give it a Go board and it produces a Go move, if you iterate that many times, results in good performance at the game of Go. And so we're still fundamentally doing the same thing, where we're just searching over a large space of parameters, trying to find those set of parameters which in fact result in good performance on some data. But now we sort of have this interactive setting where what good performance means does it have the ability to actually play and win over many series of interacting with an environment. And we use various algorithms for being able to search over that space in a sort of meaningful and effective way. But it's still essentially doing the same thing. We're still searching over this large space of possible parameterizations, trying to find some algorithm which has some particular property on some data. Okay, and so this is often yields great results in practice, like stuff like AlphaGo, but structurally it's doing something very similar, where we're still trying to find the simplest algorithm. It's just now we're sort of trying to find the simplest policy, the simplest sort of way to act in an environment. Okay, now probably, I think, if you're familiar with, a lot of the big advances of machine learning, you'll be familiar with stuff like AlphaGo. But you'll probably be even more familiar with language models, large language models, that probably are the most, well-known and maybe probably the most powerful of, the existing sorts of models that exist today. And they're really good. I think that if you have never interacted with a large language model before or haven't really interacted with one very much, I think there's really no substitute to just doing it yourself. I think that the best way to sort of get a handle on what it is that these things are and effectively how they work and what they're capable of is find one online that you can interact with, ChatGPT, whatever, and just sort of talk to it, ask it questions. I think this is a really valuable experience for anyone who's interested in trying to understand AI and how it looks right now to do. But long story short is they can do a lot of really impressive stuff, right? So what we did is we just found the simplest algorithm which fits the entire internet, effectively. And it turns out the simplest algorithm that fits the entire internet, can reason, it can write stories, it can talk, in a human sensical way. It can do a lot of really crazy stuff. Okay, but fundamentally, what it is that it's doing, is hard to understand because now we have a data set that is so large and so complex that the simplest algorithm that is able to fit a data set that complex and that large, well, it need not be that simple of an algorithm anymore, right? Once we put that constraint that it has to be the simplest algorithm that fits the whole internet, that's a strong constraint, and it means that the resulting simplest algorithm might still be very complex and very complicated. And so, unfortunately, our understanding of what mechanistically large language models do, what happens when you take the simplest algorithm that fits the whole internet is quite poor. And so we'll talk a little bit later on in the lecture series after a bunch of lectures. We'll return to this question. We'll talk a little bit more about what it is that large language models might be doing mechanistically. But even then, all I can promise is speculation. So we're going to speculate a little bit later on about what it is that these things might be doing, but it's complicated. And our understanding of exactly what mechanistically they are doing is not super great. What we have is just, well, whatever the simplest thing is, that fits the internet, whatever that is. And even then, it's like, well, exactly what the inductive biases. Inductive biases are just a name for whatever it is that determines the sort of metric of simplicity in neural networks, in machine learning. Whatever those inductive biases are, whatever that metric of simplicity is, even then we don't fully understand it, right? It's not exactly the same as human simplicity. It's some notion of simplicity that does in fact a good job. And whatever that notion of simplicity is, there is some algorithm which does a really, really good job on that we find when we train these sort of massive language models. And in practice, what we see is that whatever that is, it does a really good job in practice, but what it actually is doing is quite difficult to understand. Yeah, question?
What do you mean when you say training an algorithm that fits the entire internet? Can you comment a bit more on the data set that when we compose, where we train these language models, and how is that literally training the entire internet?
So it's basically true, right? There's a couple of caveats here in terms of exactly how scraping is done, exactly how data set creation happens. But basically, the sort of standard state of the art currently for training very large language models is make a massive scrape of as much of the internet as you can find, try to do some amount of filtering and extract out the sort of data points which are actually going to be most useful and relevant, and then just train on them. Find some simple algorithm which is able to fit all of internet text, which is able to predict what the next word will be in any situation that it finds itself on in the internet.
That is Western internet, right?
What?
That is the Western internet.
The Western internet. No, it's not just the Western internet. In many cases, scrapes will exist of, basically anything that is, publicly available. It really will depend on exactly what, case. Sometimes there will be cases where people will filter to just English text. That's not uncommon, but it's not always what's done. So, it just sort of varies on exactly how you want to train your model and what you want it to be able to do. If you're mostly interested in it just being able to interact in English, then, it's going to be, wasteful to sort of train on a bunch of things that are not English. And so oftentimes, you can try to, just filter down to English, but that's not always done. So, it really depends. But essentially it is, take a really large scrape of, a bunch of text from the internet that is as high quality as you can make it while still having a huge amount, and then just spend millions of dollars training, some really, really large parameterized function that in fact results in good performance on that data set.
Obviously, the answer to this is going to have to be just speculative. But given what we learned before about double descent and how eventually the model reaches a point where the simplest function it can understand that fits the data the best is just memorize everything, it seems that current language models have not reached that point. Do you think it's possible that we could end up with like GPT-4 or GPT-5 or something that actually does just memorize the entire internet, and then GPT-6 would actually be worse than GPT-5 if they continue to expand it?
So that's only possible if the sort of people building these models sort of, made a mistake, because everyone knows, the graphs that I was presenting, right? And so we sort of have actually pretty good ability to be able to predict and understand where the various basins are going to end up on those graphs. And so you can extrapolate and pick exactly how many tokens to train on, how large of a model to use, for the purpose of ending up in a spot where your sort of scaling predicts it's going to have good performance. And so that's what people will do in practice. And so if you sort of just did the naive thing of just like take the exact same model and make it bigger and bigger and bigger and bigger, while like changing no other properties of it, then yes, you would encounter that. But that's not what people do, right? They actually change the amount of data and other factors as you sort of make the model larger to prevent that from happening. And so yeah, if you were sort of doing something naively, you would see this, but because people are not doing it naively, you shouldn't see that.
So basically, you would end up with this point where the model might need to either need more data or a lot more compute to get better performance, but we would know that instead of just spending millions of dollars on training a model and like, oopsie.
Yeah, I mean, so it is possible that like some of these sorts of scaling laws could break, things could happen differently than we predict, but we do at least understand this phenomenon enough that it's unlikely that it would just be a situation where we just trained it accidentally into the sort of wrong regime. There may be other cases where performance decreases for other reasons. So there are examples of what's called inverse scaling, where as you sort of scale up your language model, various different metrics that are of like desirable properties can go down in certain cases. Oftentimes, one example of this is cases where there's sort of a misleading answer to a question, where the model will sort of be, larger models are often better at being able to sort of convince people of these misleading answers, and so it can sort of do worse on a like how good is the information quality as the model gets larger sometimes. But that's still, it's not a case of like we just sort of like totally screwed up and like trained the wrong size of model. It's a case of okay, there's some sort of more complex thing happening in what it means for a simple function to fit this data, right? There's something going on in how the sort of function operates that causes it to sort of have this particular behavior change as we get sort of simpler functions that are better at fitting the data. Cool, okay. So we're gonna sort of shift gears now for the last part of this talk. So we've talked a bunch about machine learning, and we've talked about this basic process of taking these large data sets, finding simple functions which do a good job on the data set. And the sort of fundamental problem that we've encountered is that we often can't know exactly what it is that the sort of simplest function that fits a data set is doing, because we don't fully understand what this notion of simplicity is, how it operates, and sort of what it corresponds to in terms of what the actual algorithms are that these models end up implementing. And so I want to sort of take a step back and ask a sort of basic question, which is, what is the worst case scenario, right? what is the worst possible thing that it could be that these models are doing that we would be concerned about? Given that we don't know, right? If we are in a situation where we're building really powerful systems and we don't understand structurally what those systems are doing, I think it's prudent to take a second and sort of try to understand okay, how could things go wrong? What are the worst possible scenarios for what these models could be doing? Okay, so that's part 2 of the first talk. So what we're going to be talking about here is this notion of instrumental convergence. So I'm going to borrow an example from Stuart Russell, who's a professor of AI at UC Berkeley and likes to talk about this sort of thing a lot, where he sort of uses a sort of analogy to illustrate the sort of why we might generally be concerned about the situation where we have very powerful AI systems in the world and situations where they start to get more powerful than humans. He sort of calls this the gorilla problem. So the question that we sort of that he likes to ask here is, well, what is the second most intelligent species on the planet? I mean, pick your favorite great ape. I'm not going to claim it's definitely the gorilla. I'm not an expert, but whatever. We'll suppose that it's it's the gorilla. Substitute chimpanzee or whatever other animal you prefer. It's probably something like that. Is the second most intelligent species on the planet after humans. And so what is their fate, right? What determines the ability of the gorilla as a species and of individual gorillas for them to be able to thrive and live good lives and do the things that they want to do? And the answer is, well, it's mostly not about the gorilla. It mostly has very little to do with what the gorillas do and almost everything to do with what we do, right? The ability of gorillas to continue to have a habitat, to continue to exist and not be endangered, to thrive, to be able to find food and resources and live their lives is dependent on our ability to let them do that. It's dependent on things like environmental measures, on things like global warming, on things that like environmental policy that the gorillas probably don't even understand or comprehend or could comprehend. But that's what determines their fate, right? The thing that is going to eventually determine the fate of the gorillas is the way that we treat them and the general policies that we build. It has nothing to do with the gorillas. And so this is a sort of maybe striking example of a case where it's not great to be the second most intelligent species on a planet. Even though maybe people have tried to communicate with the gorillas, it's not like they're totally incapable of communication. They clearly have the ability to have meaningful preferences in some cases. But their ability to act on those and actually is highly constrained by whatever however we treat them. And so if we are in the business of building systems that we expect maybe will eventually be more intelligent than us, we should be concerned that we may end up in a similar situation with the roles reversed, where if we are building systems which are more intelligent than us, that our fate may lie more in the hands of those systems than it does in ourselves. And that's a concern, right? If we're talking about originally what is the sort of whole point of this? Well, we want to avoid existential risk. We want to avoid situations where humanity is disempowered, where we no longer sort of are able to control our own destiny. And so if we are in a situation where that control is wrested away from us in the same way it's sort of wrested away from the gorillas, we're concerned. Okay, so this doesn't say necessarily that we should be concerned. Maybe AIs will treat us well, or maybe we don't know, right? We don't know what they're doing, but we want to understand the worst case scenario. So we want to understand, okay, if our fate is in the hands of these sort of very powerful AI systems, we don't know what they're doing, but what things could they be doing that would be bad for us? So I have here a Minecraft map, and I sort of want to consider a thought experiment. So let's say we are at spawn, we're at the center of this Minecraft map, and we have some objective. Maybe we want to build a house in the top left quadrant. We want to go thousands of blocks away and build a house. What do we do, right? What's the best strategy for us in building that house? Well, what we're going to have to do is we're going to have to build a boat, chop down some trees, use those to build transportation. We're going to have to gather resources, start mining gold and diamonds. Okay, those are some of the things, right, that we would have to do if we were to try to build a house on the top. Okay, but let's say instead of trying to build a house, what we wanted to do instead was blow up with TNT the entire chunk in the bottom. okay, that's a totally different goal, right? It involves completely different, objective. But what's the best way to accomplish it? Well, we're still going to need to be able to get ourselves down there where we want to be able to blow things up. So we're still going to have to be able to, build a boat, gather resources to be able to transport ourselves. And we're going to have to get all the TNT from somewhere. So we're still going to have to mine things out and, kill a bunch of creepers and gather a bunch of resources so that we can actually build the TNT that we need to be able to blow the thing up. So it looks pretty similar, right? We have these very disparate goals, in totally different places where we want to do very different things. But in this sort of setting, they require inputs, resource inputs, which are very similar. They require sort of, same basic resources to accomplish these very disparate objectives. And so there's sort of a basic structural property of the world at play here. And an important, so an important thing to point out is that this sort of structural property here that we're talking about, it's not a property of, the goals per se. It's a property of the world. It's a property of the fact that in Minecraft, there are resources, items, blocks, things that you need to be able to do almost anything in the game. And because of that property of the world, almost anything that one might want to do in Minecraft requires these same resources. And what that means is that if you have multiple agents in the world that might want to accomplish the same goals or might want to accomplish completely different goals, they're still going to have competition for the same basic resources. Okay, so I'm going to borrow another example from Stuart Russell, who likes to call this problem the sort of problem of you can't fetch the coffee if you're dead. So the idea is, you have, some model, some agent, some system, and it has some goal, whatever it is. In this case, it wants to fetch coffee. And the problem is, well, fetching coffee has, basic resources that you need, one of which is your own survival. You need to not die, right? And so in the Minecraft example, in all of the cases, I'm going to probably need to get some gear, to protect me, right, against enemies. In this case, I need to make sure I don't die if I'm going to fetch coffee. And so there's basic structural resources, basic things that are necessary to do almost anything. Anything that you might want in the world requires the same sort of basic inputs in many cases. And of course, this is not just true of Minecraft, it's true of the real world as well. So, there are basic resources that exist in the world, materials, matter, energy, neg entropy, atoms of various different varieties, elements, all of these things, that exist in the world that one needs to do almost anything, right? Anything you want to build, anything you want to accomplish that happens in the world requires the same sort of basic resource inputs, almost regardless of what it is. This sort of structural property of the world, this sort of basic property of the world that, different, very disparate goals can require the same resources is a property we call instrumental convergence, where the same sort of, all of these very different goals can converge on the same instrumental goals, where, instrumental here is just a thing which is useful for accomplishing another thing, right? And so the things which are useful for accomplishing other things tend to be very convergent across sort of many different possible things one can do in the world. One thing I will point out is that, I did sort of make a hidden assumption here, which is like, well, why would your AI even want to accomplish anything in the world at all? And that's an interesting question. It's one that we're sort of going to be talking a little bit more about in the next two talks. But the thing I will say right now is, well, okay, we don't know. It might not be. It's very unclear, whether we will train systems that are trying to accomplish things in the world. But the point is that if they are trying to accomplish things in the world, and we don't fundamentally understand why they would or would not be, almost regardless of what it is that they might be trying to accomplish, we're concerned, because humans want those resources too to be able to do the sorts of things that we desire. And if we are in competition with AI systems for those resources, it could be quite tricky. Okay, question.
So, Here
you go.
But what if my goal is literally just to make coffee within 5 minutes? Surely it would be easier to just make the coffee than to try to take over the world and steal all people's resources.
Yeah, so I think that's a good point. I'm definitely not claiming that like any possible goal that you could have would always yield your model, trying to take over the world. I think that there's a couple of things that we can say here. So one is like, well, okay, we're trying to think about the worst case scenario. We're trying to think about, okay, how many goals are there that result in bad things? And even in that case, there's still some resource competition. There's some resources that you need. You need to like exist for enough time to get the coffee for 5 minutes. You need to be able to do enough things in the world to accomplish that goal. And if you're really, gung-ho about that goal, then, you also have to do other things like, protect yourself, build, as many defenses, against possible ways in which you could fail your 5-minute task. Make sure that, you're as likely to complete that task as possible. And those things could yield increasing sort of, resource consumption. But the general point is not that anything that your AI system could possibly be doing is going to result in it wanting to, kill all humans. I think that's not true. I think the point, though, is that we don't know what it is that they are going to be doing structurally. All we know is something like, okay, it's going to be something like the simplest algorithm which fits some massive data. We don't exactly understand what that algorithm might look like or what it might be trying to do in whatever sense trying means. And it's conceivably possible that it could be trying to do a very large variety of things, many of which, if the things that it is trying to do involve accomplishing something in the world, result in outcomes that we might not like, right? Result in outcomes where they are competing for resources with humans, resources that we would like to use to make our lives better instead. And so there are many cases where that resource competition is maybe okay, right? So maybe we want, if our AIs are competing for resources on our behalf, they are trying to gather resources for us in the way that we would want them to be doing so, then maybe we're okay, right? But there's a lot of possible things they might be trying to accomplish. Almost anything, any sort of randomly selected thing in the world that you might be trying to do, where if that's not exactly the sorts of things that we want, that humans might end up in not so good position. And a thing that I'll point out about this is, if you're interested in this basic phenomenon of instrumental convergence, it's something that shows up not just in Minecraft, not just in the real world. It's a very basic structural property of almost any environment. So even a randomly chosen environment where you just randomly choose what the states are in that environment and what the transitions are between different states, has the property that optimal policies in that environment, the sort of best way of solving that environment for random goals, random desired states, will result in a property where the optimal policies will tend to seek power, where states that are powerful in the sense that if you go to that state, you have the ability to sort of unlock a large variety of different new states that you could go to from that point, will be sort of convergent for almost any way of accomplishing any random goal in a sort of most optimal way. And so this is, we can sort of prove and study this mathematically. And so if you're interested, you can take a look at the Optimal Policies Tend to Seek Power paper. But the basic, sort of structure here is sort of very fundamental to almost any of these sorts of environments. It's just the case that, in any case, in any situation where there are sort of, general properties, states, resources which are useful for like doing things, then those resources are going to be in competition and they're going to be, useful for a wide variety of different possible, things that one might want to accomplish. And that's the core concern here.
Or there being some research a couple of years ago around satisficers rather than maximizers, where they're just trying to get to like a specific threshold, maybe capping their instrumentally convergent goals. I'm also kind of drawing a parallel here to wanting to create a system that eventually is happy turning left rather than going right, kind of staying there. Is there also kind of an element here of the tragedy of the commons problem, where even if we knew how to correctly and successfully do that, systems that go right are simpler in some sense, drawing back to kind of this parallel of machine learning producing simpler systems, and so there's this really heavy pressure and impetus towards at least some of the systems always potentially going right, and therefore kind of failing on tragedy of the commons problem?
Yeah, okay, a bunch of questions there. So I'll start with the satisficers. So I think satisficers is a really interesting idea. For people who are not familiar, the basic idea is, well, what if you try to accomplish a thing, right, and then stop? Sort of similar to the proposal that was talked about earlier about the, what if you get the coffee in 5 minutes and then you're done, right? You sort of have some level at which you want to achieve your goal and then you stop. It's a really interesting idea. I think the main, most fundamental problem is, what if that's not the simplest way, right, to fit the data, right? We're sort of in this setting where we don't get to pick exactly what the structure is of the algorithm that we find when we do machine learning, right? We get some control over it, right? We get a lot of control over the data. We get a lot of control over the architecture. But how the architecture and the data combine to find the sort of simplest algorithm that fits that data is a complex process that we don't get a lot of control over, right? It depends on these basic structural properties about what algorithms are simple. And so it may be the case that we can find mechanisms for consistently producing satisficers rather than optimizers. And it may be the case that we can't. I think currently, I don't know of a way that you could consistently train models and believe that they're definitely going to be satisficers. I think that's a really tricky thing to be able to do. you can certainly do things where you sort of train models on fixed reward schedules where they can't ever get more than some level of reward. But even in that case, you can end up in situations where your model wants to maximize the probability of it achieving that level of reward, right? Where it wants to, maximize the probability that it's able to, get at least that much of whatever, it is that's trying to accomplish. And so, it can get very tricky in terms of, actually getting a thing which is well described as satisficer. And even then, if I'm training on a reward, which is just like, whatever the loss that I'm training it on, I don't have a guarantee that my model in some sense cares about the thing I'm training on. All I know is that it is some simple algorithm that fits the data well. And that could fundamentally be doing almost anything. And so I think satisficers are an interesting idea, but it's how to actually get them to work in practice is unclear. And then let's see. Going on to other questions about the tragedy of the commons, what this might look like, sort of, in terms of, in practice, sort of how this plays out. I think that it's really sort of unclear. I certainly think that you can sort of think about what's happening here as a sort of tragedy of the commons scenario, where it's like, okay, you have a bunch of resource competition. It would be really nice if we had some ability to, be able to sort of, manage those resources in a way that wasn't just, whatever the most powerful, intelligent species is able to just, control over them. But of course, we don't have, some mechanism that we can use to just sort of constrain any, possible agent. Certainly, we have mechanisms that exist in the world today that we can use to constrain humans. We have things like laws and governmental institutions, that we use to create a society that constrains humans in particular ways. But we don't necessarily have the ability to constrain some arbitrary intelligence, right? You can imagine, certainly there are there are sort of, in some sense, rules, maybe among gorillas, right? Where there are things that, they punish, defectors against their, if you try to do something in the, gorilla society, maybe they'll, cast someone out of the group or whatever. But, those have almost no bearing on us, right? We don't care, that there are, particular, ways that gorillas punish other gorillas. That has no bearing on us because we don't have to care. We are so much more powerful and intelligent than the gorillas that, it doesn't matter whatever structures they have. And so it's possible we could build systems in ways that are able to constrain, a society of, humans and AIs, having very powerful, intelligent, AIs in the world. But it's tricky, right? We can't just do it via the same, mechanisms that we use to constrain humans because, those mechanisms are limited by, humans actually being willing, to cooperate and for us to be able to have the ability to, make them do what we want when they refuse to cooperate. And it may be very difficult to do that if you have a, system that is substantially smarter than you that can, outwit you in any situation. And so that's potentially a concern. Okay, so if there's any last questions at the end, I can take a couple of last questions, but that is it for lecture 1. We're gonna, there are still a bunch more to talk about, and we'll get to those later. But that is the end of the first part. Okay, final questions.
So you mentioned at the very beginning of this talk that a lot of the assumptions we'd be making was that prosaic AGI, but that prosaic systems could lead to AGI. How likely is this actually to be the case?
Yeah, that's a great question. So I think it's very unclear. Predicting the future is always, a very tricky thing to do. And in many cases, that's sort of the business that we're in, right? When we're talking about this sort of thing. There's a couple of things that I'll say. So the first thing I'll say is, in the case of prosaic AGI, I think that our sort of best guess should be it's probably going to be something like what we have right now, right? Because it's so difficult to try to predict and understand exactly, what future developments might exist. By default, we should guess, well, okay, it's not going to be the same as how things work currently, but our best guess should be how things work currently because we can't predict exactly in which direction it is going to vary from where we are right now. And so I think that trying to start from if it was like current systems, how would we be able to understand what to do in that situation? is a really good starting point. And as new advances come and we sort of find new ways in which AI is developed, we can change that understanding to suit those new directions. But by default, we should expect that those new directions are probably going to be something similar to what exists right now. And so understanding what exists right now is sort of a key input into being able to understand things in the future. And then the other thing I'll say is that it is very difficult, right, to predict exactly when things are going to happen. But I think that, right, because all of this is a prediction. But I think that in many cases there are some things that you can predict, right? Predicting exactly when something is going to occur is very difficult. Predicting that something will occur is much easier, right? So we can understand, okay, AI continues to keep getting better. It continues to keep getting more intelligent. As long as that trend continues, at some point it will surpass humans. At some point it will become the most intelligent thing, and we'll sort of have to deal with the consequences of that. Exactly when that will happen, where do those graphs meet, what is the slope, how do they, change? That is very tricky to predict. But the fact that it will happen at some point, barring some other existential catastrophe that wipes out humans, seems quite clear. There's no fundamental barrier to us being able to build systems that are smarter than us, and even a very large number of systems that were the same intelligence level as humans would also be equivalently existentially dangerous. And so at some point it has to happen. And exactly when, I don't know. And I'm not going to try to speculate a bunch on when, because I think it's just such a tricky thing to do, and a thing that sort of involves a lot of analysis and also just a lot of opinions, and it's very difficult. And so I think that speculating on when is hard, but I think that we can talk about these sort of general properties, and we can try to sort of approach the task of being dealt with this problem of how do we deal with the problem that in the future these very powerful systems might exist and might be dangerous, in as effective a way as we can, which is, well, we have to do something because the problem is concerning and we want to try to address it. And so we're forced to try to make whatever predictions we can that are as good as possible. And so we can try to build upon what we have right now, try to understand how things work, and basically chart a course for being able to understand future things. But it's hard, and so one of the things we'll talk about sort of later on in some of the other lectures is telling multiple stories, right? Where like we don't know exactly how things are going to play out, and so we can imagine multiple different ways in which sort of things go. So for example, one thing that we talked about a bunch here is we're really uncertain about exactly what the inductive biases are, right? Exactly what the measure of simplicity is that models use. But we can sort of imagine, well, what if we think about multiple different possible ways that it could be? And then under different scenarios, how would things play out, And so we'll sort of use that as a mechanism later on for trying to understand particular scenarios, because that's a way to sort of deal with our uncertainty. We don't exactly understand what it is that is true, but if we think about multiple different possible options, we can see what's convergent between those options. And that sort of can tell us what things are really likely in practice.
You mentioned one of the things you encourage people to do is to pick up a large language model like ChatGPT and play with it directly just to get a sense of its capabilities, its outputs. Seems like you're at the talk, the actual process of understanding basins and what kind of pathway through basins is taken is also very important to build an intuition on. How do you recommend people build that kind of intuition? Through maybe toy models or through more kind of theoretical understanding of what's going on? Like, what's the best way to build an intuition of that?
Yeah, that's a really good question. I think part of the problem is that it's just not super well understood what exactly it is that that's sort of happening with those basins, and so I think that maybe the best way to sort of get an understanding there is just looking at what some of the models are that actually exist and how they work and what they do. And sort of trying to understand what is this metric of simplicity, right? It's determining what these models are and how they're functioning. Certainly playing around with different models and just understanding in a lot of different cases when we train on various different scenarios, what things does that result in can sort of help. But yeah, it's just really tricky. Okay. If that's it, we can call it there, and we'll have another lecture, hopefully, coming up pretty soon.
Tomorrow, perhaps.
I can't do tomorrow, I don't think. We'll talk about it.